We usually imagine metals as rigid, unyielding materials. To break down iron and turn it into a liquid, you must expose it to extreme industrial temperatures well above 1500 degrees Celsius. But there is a metal that defies that expectation completely. If you hold a small, solid piece, the ambient warmth of a human palm is enough to melt it into a pooling liquid. The sight of a solid metal flowing like water at temperatures we consider comfortable illustrates the remarkably narrow boundary between gallium's solid and liquid states. This strange substance is gallium, element number 31 on the periodic table. Its liquid behavior comes down to a remarkably low melting point of just 29.8 degrees Celsius. Because that threshold is so close to a standard room climate, the slightest shift in temperature dictates whether it sits on a desk as a rigid block or flows as a liquid. While its sensitivity to heat is unusual, its history is even stranger. Scientists knew exact details about this metal long before anyone had actually seen or held it. Decades before gallium was physically isolated, the Russian chemist Dmitri Mendeleev was developing his early version of the periodic table. This historical document shows his attempt to organize elements by atomic weights and properties. Mapping the patterns, he noticed mathematical gaps. Instead of assuming his chart was wrong, Mendeleev left placeholders, predicting a missing element he called Eka aluminum and calculating its approximate atomic mass. In 1875, French chemist Paul-Émile Lecoq de Bois-Baudran discovered and isolated gallium. When its actual physical properties were finally tested, they matched Mendeleev's blind mathematical calculations almost exactly. Scientists realized the periodic table was an accurate, predictive map of reality, capable of detailing materials that had yet to be found. Despite its importance, pure gallium is extremely rare in the Earth's crust and is not traditionally mined on its own. Instead, it is extracted as a byproduct during the heavy smelting and processing of other metal ores, specifically zinc and aluminum. Once isolated, it exhibits properties that run counter to almost every other metal. While most substances contract as they change from a liquid to a solid state, gallium expands as it freezes. Storing it in a rigid container often results in shattered glass or split seams. It also has a uniquely destructive relationship with aluminum. If liquid gallium rests on an aluminum surface, it penetrates the atomic structure of the host metal, interfering with its bonds and severely weakening the entire object until it crumbles under slight pressure. It is a chemical contradiction, a metal that acts like freezing water in a glass jar, capable of silently destroying one of humanity's most common industrial building materials. Outside of these destructive laboratory interactions, gallium has a secondary, highly productive capability when combined with other elements. It readily forms alloys, creating compounds like gallium arsenide and gallium nitride that serve as cornerstone materials in modern electronic manufacturing. These specific compounds manage high speed, high frequency, and power electronic processing at levels that standard silicon materials simply cannot sustain. Certain gallium-based semiconductors also have the unique ability to efficiently convert electrical energy into light. This property makes it a driving force behind lasers, LEDs, and modern optoelectronic devices. The unstable metal that melts in your hand and ruins solid aluminum structures operates as a highly reliable backbone for our advanced digital infrastructure. From a placeholder in Mendeleev's 19th century calculations to the physical core of today's digital infrastructure, gallium connects historical chemical theory with modern technological reality. Element 31 reminds us that the elements that break our expectations often reveal the clearest insights about how chemistry actually works. If you enjoyed discovering the strange side of the periodic table, subscribe to Atomic 118. We are exploring all 118 elements, and every element has a story worth discovering.